maybe you have to accept this. Yeah. Okay, so it's a great pleasure to have today Patricio Salgado-Rebolledo. So he is now postdoc in Wrocław University. He got the PhD both in Chile and Brussels, ULB University, and his PhD supervisor was Jorge Zanelli. This is one of the three famous, one of the names that appear in the BTZ black holes, among other things, of course. And after that, he did the postdoc in Chile, and then another postdoc in Brussels, and then finally he moved to Poland for in Wrocław. So, and he's going to talk today about fractons and in curve space.
Thank you. Thank you also for the opportunity to give a talk here and present my research. So, first of all, I'm not an expert on fractons. This is the first time I go into this subject, so I'm also eager to learn if you have comments about this type of systems. That could be interesting. This is a work in progress in collaboration with Francisco Peña Benitez also from Wrocław University of Science and Technology. And as Gian Domenico said, I'm going to be talking about fracton gauge fields in curved space from higher dimensions. So the motivation to study fractons comes from topological phases of matter. So topological phases of matter is a subject that has received a lot of attention in recent years. Exotic phases of matter, such as topological superconductors or the fractional quantum Hall effect, for example, admit descriptions in terms of field theory in certain cases. So the same people started also looking for field theories that could describe the low energy regime of this type of topological phase of matter. And the subject that I am interested in, that we're interested in Wrocław, is how to understand this type of excitations that I will show you here in the case space is curved. So the outline of the talk is this one. I'm going to first briefly review Fracton electrodynamics, which is a generalization of Maxwell theory for the case of fractons, which I will also show you what they are. Then I'm going to try to define these excitations in curved space. I will show you the problems that appear when one tries to do that. And then I will go a little bit more in details into the symmetries of these systems, how they can be connected to relativistic symmetries. And finally, by means of dimensional reduction, I will show you how fractal electrodynamics can be derived from a higher dimensional theory. And in this case, it's necessary to use something similar to a Kaluza-Klein reduction. So what are fractons? Fractons are excitations that have restricted mobility. They are usually immobile in isolation, but they have some mobility when other excitations are present. They appeared first in theoretical lattice models. Here I mentioned three examples. So the HACO, the X-cube, and the checkerboard model. In this type of systems, what happens is, like in this picture, I try to show this idea that a fracton alone is immobile, but when it's possible to form something like a dipole, then mobility can occur. So just pictorially, this is one of the models that I mentioned before, the X-cube model. So it's a really complicated system with a really involved Hamiltonians. It's constructed out of operators, Pauli operators. For example, the terms here, B's are defined as the cubes. They involve 12 Pauli operators. The A's are defined as the vertices, and they involve four Pauli operators. So what happens here is that if one creates fractons, which are pictured here in these cubes, they cannot move in the lattice unless one creates more. But when two of these excitations are created in a pair, then one can construct something like a hopping operator and make this excitation move, but only along a plane. So sometimes fractons can move, but they can move only along, let's say, subdimensional subsystems or of the whole system.
So what are the 12 Pauli operators? What you
Well, I don't have the explicit expression here, but you need to put together 12, you need to create 12 excitations in this cube.
so they're not associated with you. You're putting the Pauli operators at a vertex.
Well,
Yeah.
at each cube, yeah, and also on the vertex, yeah, and the edges.
You're putting them on the edges.
Yeah,
I mean that you're four Pauli, you have four Pauli operators. So just maybe I should understand what four Pauli operators are first.
yeah. Here you have a product of four Pauli operators, but yeah,
You mean a product?
yes,
Ah.
yeah. So it's really yes,
Different
yeah,
Pauli matrices at different sites.
yes, that's right.
Ah,
So yeah, it's
okay.
really ugly coming part, but
And
this
U and B is a product of 12 Pauli matrices.
sorry,
It's a product of 12 Pauli
yes,
matrices.
that's right.
How many sites involved?
Hmm?
How many sites are involved in B?
Oh, well, these operators, okay, maybe I should have looked for a different picture, but you need to create 12 different excitations here along the cube. Yeah, I didn't go into details in this.
B
model.
should be the vertex.
Yeah,
C the vertex.
exactly.
C
And
is
C
the
is a
side.
sum over the cubes. So see, yeah,
The
see that.
sides. Side for your level
Yeah.
each.
B is the vertex, and,
Yeah,
and there,
C.
but there are 6 vertices on a cube.
Yes.
So you're talking about the 4 vertices from either the top or bottom of the cube,
That's right.
and the 12.
Well, it's a complicated construction. I really wanted just to motivate this idea, I mean, just to show you that there are these type of models that have restricted mobility excitations. But I don't really want to go into details into this model. I want to show you like the field theories that can capture some of these properties.
Yeah, I'm kind of
Yes.
confused as to the 12. Why there? I can see that there are 12 edges,
Mm-hmm.
but you're counting them twice in comparison with the 4 Pauli ones.
Yeah. Well, it was really long to write this Hamiltonian in an explicit way. I don't know, gentlemen, if you have a bit more.
It's like a implementation of the correct code.
Mm-hmm.
So you put in each, okay, so again, G is the side, and so you should put yeah, so 12 because in of the cube, no? As
There's 12 edges in the
Yes.
cube.
Yeah, you have to multiply all of them, no? And then you define B for each side.
Okay.
So that's why it's sort of
So you multiply all of the edges on
yeah,
on
and
the
then
cube.
you sum of each side.
And what was the A again? Then you have that.
The A is yeah, it's the yeah. I think yeah. So it's validated with each one. Yeah. People there are 4, 1.
And there are 3 of them meeting at a vertical, seems what you're saying, as opposed to 6.
Mm-hmm.
It's a very complicated model. That's one.
Yeah.
No, it's very complicated. So
There are no experimental realizations of this type of model.
It's not very theoretical.
Yeah.
Some error correcting, not using a realization.
Okay.
Okay, but what I'm gonna be focused on during this talk are field theories that capture this behavior in the sense that excitations cannot move, but dipoles, for example, could be able to move. So usually these field theories, these are not continuous version of these models either. These are completely different field theories that they share some properties like this restricted mobility. So they usually involve a higher rank tensor. Like for example, the simplest case I'm going to show you is a gauge theory involving a rank 2 tensor, completely symmetric. And it is possible in these cases to formulate something like a gauge theory.
You're going to take A to be a symmetric tensor.
That's right.
Traceless?
Not necessarily. No. Yeah. So just to motivate this construction first, gonna briefly, this is something that we all know, it's just Maxwell theory. So Maxwell equations can be obtained from an action of this form, where the field plane can be written in terms of a vector potential and a scalar potential. And of course, there is a gauge symmetry in the sense that one can transform the potentials in this way with a function that depends on the space and coordinates, and the action remains invariant. So, what happens? Yeah, I don't know what happened. Let me see. Do you still see the screen there?
We see the same as.
Can you go
there.
out?
It's
Hmm.
it's white at the next.
Oh,
Are they white?
yeah, I don't know why. Also like that before.
I think you're not using a PDF or something. Just
No, it's not white. What you have? So
Yeah, let me.
can you open?
I will close it and open it again. Okay. So
You're using Adobe, but you can use another to show the PDF.
Yeah,
maybe.
I've got a Mac as well, and whenever I open PDFs with Adobe, it goes mad.
Yeah, let's go for preview. Yeah. Okay. Can you scroll?
Okay, this is
Okay.
fine.
Put
So-
full. Yeah.
How can I go here? Push
And the last one.
Okay.
Yeah, okay.
So if one introduces a current, yes.
Okay.
Good. Yeah. If one introduces a current that couples to the electromagnetic field, then one can derive the conservation of the charge from the continuity equation in the usual way.
Can you go back?
Yes,
No, this is just Maxwell. Sorry.
that's right. No. Okay, so what Fracton realized some years ago is that one could try to generalize this construction and ask for the conservation of more charges, not only the electric charge, but for example, the dipole charge as well, which can be defined this way. And if one asks for these two charges to be conserved, not only the electric charge, then excitations cannot move, but the dipoles can move. So in this case, if one introduces a new charge, Ki, now these charges don't commute anymore with the translations. There is a non-vanishing commutator between K and the translation operator that gives Q in this way. And now if one adds rotations to the system, then internal symmetries now are mixed with the space-times, with the spatial symmetries. And they form an algebra that we will call the Fracton symmetry. So these are translations, rotations, and the charge associated to the charge and the dipole charge. So in the same way as before, the conservation of these two charges here can be derived from a generalized continuity equation that involves, instead of a current described by a vector, now it's a symmetric tensor, and it involves also an extra derivative. So people have generalized this idea by introducing more charges, and this is what is called the multipole algebra, which was developed by Gromov also a few years ago. So in principle, one could demand for the conservation of higher moments and obtain, even in the most general case, an infinite dimensional algebra.
So just, can I look back at the previous slide?
Yes.
So you're taking the first moment of
Mhm.
the density.
That's right.
Taking it to be Ki. And
Mhm.
so the Ki that is 0 and Q that is 0. So anytime there is inversion. Is there any other assumption coming to the density rho than this?
No, it's just these two things together, and the continuity equation that you can derive from. Now, what I'm going to show you a bit more general coupling.
It's sort of gauge theory for dipole symmetry, right? Like
That's
the
right.
Chart, so we need the gauge theory for the chart computation.
Yes.
It will be the new gauge theory for the dipole.
Mhm. That's right. So if one
And the integral is over three-dimensional space.
Yes, exactly.
X is the vector in three-dimensional space.
That's right. Yeah. It's fine.
So the KI is back on.
Yes, that's right. So if one wants to derive a continuous equation of this way that leads to these two conservation laws, one needs to consider a coupling now, since the current has two indices, also a gauge potential. It's a tensor, symmetry. And the gauge transformations in this case, one has to generalize the idea that comes from electrodynamics and now introduce a gauge transformation for Aij that involves two derivatives, and it's of course symmetric. Whereas the transformation law for the scalar potential stays the same. And again, in complete analogy with electrodynamics, one can construct an electric field and a magnetic field and a Maxwell-like action that is, roughly speaking, E squared minus B squared in this way. So if we go back to the Maxwell case, one can, of course, write the equations, Maxwell equations, in a covariant way by introducing the field strength associated to a four potential that puts together both the scalar and the vector potential. Then one can rewrite the action for Maxwell theory in the usual way. And one can go to curved space now by replacing the flat metric by a curved metric, partial derivatives by covariant derivatives, and write an action like this. But if one tries to do something like this for fractons, then it doesn't work in a straightforward way. So let me show you one of the first examples that was considered was the case of a geometry where the spatial geometry is curved, but not the temporal parts of metrics are just 1 and 0, like in the standard case.
So I guess basically you are saying that fractons are not non-relativistic, right? Not like Max.
Yeah, that's what appears at the end if one tries to do this.
But even before in the space, not because it's not fully covariant.
Ah, yeah, that's exactly. But
the second one.
Yeah. So in the case of electrodynamics, one can go to a fully covariant version, but we're gonna fail when trying to do it.
Even in flat space, if the gauge transformation is only, it's a Latin index, no? When you show the gauge transformation.
That's true. Yeah, but the point is, I also started with the similar type of construction for electrodynamics. Yeah.
He's saying that it's Galilean symmetry.
Yeah, exactly.
Well, at the end, not even that. It's not even Galilean boost invariant. It doesn't have any boost invariant. So yeah, that's gonna be. So yeah, it's not. So what we need to consider from a relativistic theory is not even a Galilean limit, but something a bit more strange. Okay, so yeah, one of the examples that we'll consider at the beginning was to consider only a spatial curvature. So here H denotes the spatial metric. So if one tries to introduce here a covariant derivative using the Levi-Civita connection for this metric, and one tries to generalize the gauge transformations to the curved space, the action is not turns out to be not invariant.
So I mean, you motivated it, but motivated this by your current.
Yes.
You're suggesting that A couples to this current K, or A couples.
Yeah, A couples to this current Jij. In the same way as AI couples to Ji, and from exactly.
What was the definition of Jij?
Well, it's defined in the. I don't have an explicit form here for this J, so of course one could obtain an explicit expression, for example, adding a scalar field, something like that.
But you started with a current, which was a vector current.
Yes, it's here. Yeah, that's right.
So I'm wondering what is J meant to be relevant with respect to that?
Well,
current?
here, imagine if I had like a scalar field coupled to a electromagnetic field or a fermion, then I would have some structure for this J, right? Is that what you mean?
What I'm missing is the connection between J and Q. I'm getting and Q and K.
Yeah, well, if you add this and now you consider the field equations for electrodynamic with this coupling, then you will find Maxwell equations with a source.
Yes.
Then you can derive a continuity equation from these equations by acting again with a derivative, for example. Then you obtain that, the standard conservation of the forecurrent,
Yes.
right? And from there, one can construct Q as the integral of this zero and prove using the continuity equation that is conserved.
You're saying that if I do that, a two-index object comes out somewhere along the line.
Yeah, well, if you do it with, you need to do something similar. You need to introduce this coupling together with now this type of generalization of electrodynamics, vary the equations, find the analog of Maxwell equations with the sources. They start playing with the derivatives again, and find the continuity equation that is this one.
So why is P not?
Sorry.
Why is P not?
Oh, because if you think of P as a d to the x, then you have x here.
You meant big over x,
Hmm?
You meant big over x. He is independent of x.
That's right.
So P up not.
Yeah, because here we have this integrated over the x. Yeah. But that's right. Well, maybe it would be more clear in that case to go to the Hamiltonian analysis of this model, actually.
We should be able to see it from here.
Hmm?
I was confused on that as well, but I kind of was guessing that he's thinking of moving the internal points somehow for his translation. I'm not sure what is.
Well, you could say that sign to X I, you make it Y I, then make it Y.
Yeah.
Is that what you mean?
I think it's something like that.
That could be a way to do it. Well, but the real way to do it would be to go fully Hamiltonian and to find the charges. Then the algebra follows.
Yeah, the diagonal
I thought,
will depend on the first one.
Yeah. Mm-hmm.
So you're moving the origin.
I think that's what it is.
Sorry.
Okay. So what I was showing you is that if one tries to generalize the action that I showed you, like Fracton electrodynamics, to the case of purely special curvature, then the action is not invariant under what one would naively think the gauge transformation should be. So what people did in this case, for example, to find a gauge invariant action is to replace in this action the electric field by this expression by introducing an extra field that at the end acts like a Lagrange multiplier that enforces E or Fij to be traceless, and to replace B squared by B squared minus something that goes like the trace of the magnetic field squared. So if one replaces this in the action, then one can find a gauge invariant action principle. But there is also a new gauge symmetry associated with this extra field that we introduced. But also the geometry, the spatial geometry has to be constrained to satisfy this equation, which means that the spatial metric is an Einstein manifold. And lately there have been some generalization of these results to the traceful case also, which means one can try to do something similar by generalizing this action in a different way without introducing this extra field theta. But in all the examples, that's why I'm showing you this, which is the simplest case. Anytime one tries to find the gauge invariant action on curved space, there's always a constraint on the geometry like this in this case, which means that it seems fractons cannot be defined on a general curved manifold, but one always has to pick some special type of geometry to ensure gauge invariance. Yeah, there are other examples where instead of having this constraint, you need to demand curvature to be constant. That's right.
It's unfamiliar, so
Sure.
I'm difficult keeping all of these things in my head. So Fijk was defined again. Just wanted to get it symmetry.
Fijk.
Fijk. You defined it as the.
Yeah, this is constructed in complete analogy with the magnetic field.
So it's symmetric on two indices.
It's anti-symmetric in IJ, but there's no clear symmetry between J, because okay, this one will be symmetric here in J, but this one will be symmetric in IK. So the only symmetry, like explicit symmetry, is just IJ.
And that means that the triple, the Fijk contracted with another Fijk, there isn't a unique object there that you can contract.
This one.
Yes. There's a second. I mean, it depends on.
You mean because I introduced this guy?
You can introduce.
Yeah, later people started considering these terms because there is a sort of trace you can define like this. So
those the only two invariants you can make?
No, you could also do the same type of thing. So you could take these two guys, put arbitrary coefficients. This is what they do in this paper that I am citing here. So they consider all the possible terms, all the possible contractions with arbitrary coefficients. Also for the electric field,
yes,
you can add.
What I would expect.
You could add.
How many of those are there?
I think you have these two in this case, and you have two more in the other case, as far as I remember. And then you can put arbitrary coefficients on this, and then start playing with the coefficients to find different possibilities. Yeah, but there are more. That's why there are more cases. So one can actually generalize this thing quite a lot. So another possibility to try to make this look covariant is, for example, to complete the tensor Aij to make it look like A mu nu by defining something like this. So the temporal components of A mu nu would be defined as the derivatives of the scalar potential. Then the action can be written in a nice way, like almost like electrodynamics with a curvature that also looks like electrodynamics and a gauge transformation that looks nice. But
if A was anti-symmetric, it would form actual coordinate.
well, in this case, it would be like two-form electrodynamics. Yeah, like it would. Yeah, that would be a different. But in this case, A mu is symmetric, and the fact that there is this constraint breaks the Lorentz invariance, as Gian Domenico was saying. So this is a way to write it in a bit more compact way. It looks covariant, but of course, because of the presence of this constraint, it is not.
So there is no way to put in a fully relativistic space.
No, but if one has this construction, then one can try to define something where space and time are split. For example, to construct a vector that I call tau mu, and to generalize this constraint in this way. So one should think as tau as signaling the time direction, and then the spatial metric can be used to define the rest of the geometry. But at the end, this is what people call Aristotelian geometry, that I will show you a bit more in detail later. So if one considers a metric given by this expression, it is possible to go from here to here and to have like the action written in a covariant way. But the problem is, again, like before, this is not invariant under what the gauge transformation should be on curved space. If one goes vary the action, one finds this ugly expression in terms of the Riemann tensor. But it turns out that since the second field can be integrated in the variation of A, if one now imposes this constraint on the geometry that the Riemann tensor is harmonic, then one can improve the action that I showed you before and write down this expression, which is gauge invariant only on the backgrounds that satisfy this condition. So this is another example of an attempt to write the Fracton electrodynamics theory on a curved space, and as always, there is some problem, and the geometry has to be constrained. So what we were wondering is if these actions can be derived from a gauge theory by gauging, for example, the Fracton symmetry, which I showed you before. But the gauging P usually leads to gravity because one has to introduce a gauge field associated to translation. Also, another question that people have considered actually is if these Fracton transformations can be found from something that is relativistic by imposing some constraint, more or less in the same way as I did here in the case of the action.
So can you say a little bit more about the Fracton symmetry? That's it looks like a Lie algebra structure. So
Yes, it is.
what
Yeah.
Lie algebra is it?
Well, it is that algebra. I mean, people.
Lie algebra is unclassified. So
well, people call this one, like let's say the first relation, the Heisenberg algebra, right? Because it's like generalization of the Heisenberg algebra.
yes,
So yeah, that one.
she was constant.
And then one is embedding this in, I mean, like in a bigger structure.
And what is the bigger structure?
Just adding.
The semi-direct product of the Heisenberg algebra.
It will be the semi-direct product of SOD, let's say, the
SOD,
rotations,
yes.
and that's right, in the Heisenberg algebra. And also the thing that the Hamiltonian should be usually is part of the system, but it commutes with everything. So it will be the semi-direct product of SOD with the Heisenberg algebra and R, let's say.
And the K's commute among themselves. We didn't write down the
That's
P's
right.
commute among themselves, the K's
Yes.
commute among themselves.
Yeah, usually in this like fractonic symmetries, all these charges commute among
But
themselves.
the L's form in algebra here, which is again a rotation algebra. That's the rotation, no, the P's.
Yeah, this is just the rotation
What is
symmetry.
of the K's commute? Okay,
Yes.
the rotation algebra. It's the second. Yeah, it's probably just with the Heisenberg semi-directed product with the Heisenberg. That's probably
The Heisenberg algebra plus R,
Yeah.
which denotes the time translations which are completely disconnected here. Yes. Yeah.
He's essentially X. It's essentially a condition of the term.
yes, that's
What
right.
is it? He is.
So that's what it's
He is
going
X
to
times Q.
That's where it's going to come from. It's the Heisenberg tensor rotations and translations. Yeah. Okay.
Okay, but yeah, that's
Yeah.
You can think of Q as each one.
Yeah, you can. Yes.
okay. So if one wants to understand how to construct this fractonic gauge transformations from something that is relativistic
This must
plus
be-
a constraint,
This
yes,
must be pretty close to a non-commutative field theory that people are considering.
non-commutative.
A non-commutative field theory.
Well, it's possible maybe due to the relation with the fractons, right? Sorry, with the fractal quantum pole.
There is something interesting with there is a paper by Damson that where he claims that fractons can be related to volume preserving. So to something that is area preserving thing. So there should be an emergent. It should be a still unknown connection with the geometry in a weird way. But you're right. It's still to explore this part.
Okay, so now I want to show you something a bit different. So consider, for example, this action where F is a curvature for a field that I call rho, and capital F is a curvature associated to a field that I call D. But F is modified to include also this term where E is the field line, but I will consider the flat case, so the E's are just the deltas. So that is like a really simple model that people have considered to try to understand these Fracton gauge transformations. So this toy model, let's say, is invariant under these transformations. But if we gauge fix rho to have this form, so if we fix the spatial part of rho to be vanishing, then one needs to also impose that delta rho I is 0. This fixes the parameter beta in terms of eta, and one can obtain for the spatial part of B something that looks like a Fracton gauge transformation. Also, this is something I didn't include here, but one could include currents, a current coupling to B and to rho. And using this trick, one can also recover the continuity equation associated to fractons. So just a comment. And now, if one imposes the constraint F equal to 0 in the previous model, one can write B in terms of phi and some symmetric tensor AB, and then the action reduces to the Fracton electrodynamics. So this is a way to try to understand how to construct this gauge theory from something that is relativistic And now what I would like to do is to put this idea together with the idea of gauging the Fracton symmetry. So in order to do that, I need to introduce some nonlinear contraction. So let's consider, for example, the Poincare symmetry. This is just to introduce some ingredients that I'm going to use later. So if one gauges the Poincare symmetry by constructing a connection, and one introduces gauge fields for translations and Lorentz transformations, which are the vielbein and the spin connection, as probably you know very well, one can construct the metric out of the vielbein. One can also define a curvature associated to this connection, which includes the torsion and the curvature tensor. If one imposes torsion to be vanishing, one can express the spin connection in terms of the vielbein and derivatives of the vielbein. And in that case, one can rewrite the Einstein-Hilbert action for the gravitational field. One can show it is the same as something that one could try to interpret as a gauge theory, even though it's not invariant under the full symmetry group. It's an expression that one can construct out of components of the gauge connection and the curvature. So this is an idea one could try to follow in this case if one replaces the Poincare symmetry by the Fracton algebra to construct the curvature. Then what one would like to do in principle is to construct some action principle out of the curvature. And then by imposing some of the constraints that I showed you before, or something like that, to arrive to the Fracton electrodynamics theory. So since, as we discussed before, Fracton electrodynamics is not relativistic, one needs to find a way to relate relativistic symmetries with the non-relativistic ones. So what I'm going to introduce now is the idea of a nonlinear contraction. So the simplest example one could think of is to relate the isometries of the sphere with the isometries of the plane. So to connect the free algebra with the Euclidean algebra in 2 dimensions. And this can be done by rescaling, for example, 2 of the angular momentum generators, but with the radius of the sphere, and then consider the radius to be really large. So this is like a very simple example of a nonlinear contraction, where the contraction parameter has a physical meaning. Now, there are other ways to generalize this idea to instead of considering purely spatial symmetries, to go to, let's say, space-time symmetries, and to connect non-relativistic and relativistic symmetry. So one example that is used a lot in the literature is how to obtain the Galilean algebra from the Poincare one. And the way to do it is one can rescale the relativistic generators in this way. And instead of having now translations and Lorentz transformation, one has to split translations in temporal and spatial translations. And one splits the Lorentz generators into rotations and Galilean boosts. And when one considers the limit of the speed of light going to infinity, one recovers the Galilean symmetry. And this can be done, for example, if one considers now the gauge fields associated to these generators. There is like a dual rescaling for the gauge fields. One can then construct a spin connection associated to rotations, to Galilean boosts, and gauge fields associated to temporal translations and spatial translations. They satisfy these properties, and one can construct what people call a Newton-Cartan geometry, which is usually is defined by these expressions. Here one can see that the spatial metric is defined in terms of these spatial vielbeins, and this metric becomes degenerate in this limit, and the clock form tau that I defined here becomes the null vector. So a slightly different contraction is the Aristotelian one. So one can modify the rescaling that I showed before in this way. Similarly for the gauge fields, what happens in this case is that the Hamiltonian commutes with everything after the contraction, and the Galilean boosts get completely decoupled from the other generators. So it's just a vector on the side, let's say, transforming in the way it should. So this gives also a non-relativistic geometry, which is called the Aristotelian geometry. And the questions that I showed before, I generalize now to this. So this is the type of structure that fit fractons. So when I try to write the action on a general cube geometry, I had to introduce this tau to enforce the constraint and also the special metric. And this was precisely the structure that I found, let's say, by hand in the case. So, but it can be obtained from the Poincare symmetry through a suitable limit. And another case I want to show you really briefly is the Carolian symmetry. The Carolian algebra is given by these computation relations. Now, instead of Galilean boost, there is something that's called the Carolian boost that also comes from a rescaling of the Lorentz boosts, and the rest of the generators are the same as in the Galilean case. So just angular momentum, temporal translations, and spatial translations. So here there's a similarity between the Carolian algebra and the Fracton algebra in the sense that they both have a commutator that looks like this. So if one reinterprets the Carolian boosts as the dipole and the Hamiltonian as the charge, these two algebras are isomorphic. The only problem here is that we cannot really do this because H is Hamiltonian, and we need, as I told you before, in the Fracton symmetry, also some Hamiltonian that commutes with everything that doesn't appear in the algebra, but is there. So if one tries to do here the same trick as people do in general relativity, so to use the torsion constraints to impose torsion to be zero, for the spatial part, one finds something really similar to the relativistic case, but for the temporal component of the torsion, when one tries to express the connection associated to Carolian boosts in terms of the field line and the spatial field line in the clock form, the symmetric part of this tensor is not determined. So this is different to what happens in general relativity. So if one wants to define a theory in this way, there will be an extra field in the theory that is symmetric. And this is really similar to what happens, for example, in the Fractonic case that I showed you before. If I go back to this toy model with two gauge fields, so this F, when I set F equal to 0 here to obtain B, so B also had a symmetric tensor, and the rest of this field was completely determined. So this is like really similar to what happens in the Carolian case. And the form of F that I gave you here is really similar to the temporal component of the Carolian torsion. So this is what I mentioned here. So T0, this one is really similar to the F equal to 0 constraint that I showed you in this toy model, with tau identified with rho and the gauge field associated to Carolian boost as now this vector V that, that contains the symmetric tensor IB in the previous construction.
Sorry,
Yeah.
Carolian is a log of the sense that the velocity of light goes to the opposite of earlier.
Yes, that's right.
So then it's natural then to think that something in the Carolian physics do not move, right? I mean, because they are ultra localized.
Yeah, that's also a reason why people started thinking that the Carolian symmetry is related to Fracton, because
they share the same kind of physics, not just intuition.
in that sense, yeah.
That's why it makes sense to talk about Carolian physics, because
Yes,
this kind of things that do not move.
that's true.
Eventually, the problem is to understand the dipoles.
Yeah, that's right. And also, this problem of the Hamiltonian was difficulties. That's why we had to change to this Aristotelian version instead of the Carolian. And as I will show you now, to take something that looks Carolian but on space, not on time. So if one try, there's no boost. Yeah, that's yes, yeah. So the Aristotelian geometry, yeah, exactly, would be this geometry formed only with E.
We are back to him.
Huh?
We are back to him.
Back to Aristotelian. So, because of this analogy between Carol and the Fracton symmetry, I would like to do something like a Carolian contraction, but not with the translations that, not with temporal translations, but with some spatial translation. That's why we have to go to these higher dimensional models.
Back to you're sending P naught to infinity. Confused as to what it means.
Here,
When you've kept age.
that's right. Yes. In the same with
rather
the
than setting 0 on the right hand side here, it's PACB would naturally be 0. But you want to insist that C times P naught is fixed.
that's right.
So P naught must be going to infinity. But what does that mean?
Yeah, the thing is that okay, so I'm rescaling the Hamiltonian, but I'm also rescaling the boost.
Well, I
So
guess
when I look at the
technically we could do the starting for one.
yes. So this factor of D drops from the commutation.
Sorry?
This factor of C drops in this, that's why this survives. Because you have usually translation, the commutator of translations and standard Lorentz boost give a temporal translation. But I'm rescaling these two guys in the same way.
You know, the example is P not going to create one
You probably can, yeah, but they're infinitely heavy.
But that's why I thought it would be simpler to think about this example first, because here you have exactly the same problem, no? Yeah.
Well, I mean, it is a bigger contraction.
Yeah.
Contraction, that's fine. But you want to get it as a bigger contraction of the Lorentz group.
Yes, exactly. Yeah, but these contractions are really like well understood, I would say. The Carolian and the Galilean contractions of Poincaré, they follow more or less, they are kind of dual. Yeah.
J naught A is the boost, so the boost has gone to 0 as well. As the Hamiltonian, or has gone to infinity to move it. Yeah. So,
Okay, so I'm going to use this idea of a Carolian contraction, but instead of using the temporal translation, I will add a new spatial dimension in the system and use that to define the Carolian limit. So I will introduce, instead of using P0 in the Carolian contraction, I will introduce a Pn. With n will be an extra symmetry in the system. And this is a typo here. This should be a J NA. So I will just replace P0 and J0A by Pn and JNA. And that requires to introduce an extra spatial dimension in the system that I will call Z. I will consider now a higher dimension, a five-dimensional Poincaré symmetry, and I will define this contraction that puts together both the Carolian contraction, but on the idea of the Carolian contraction for this extra spatial symmetry, plus the Aristotelian limit in the rest of the algebra. So this gives a Hamiltonian that commutes with everything. It gives me the Fractons algebra, but I'm also left with an extra vector G that is like the remnant of the Galilean boosts, and an extra generator K that are completely decoupled. So in the same way as before in the Aristotelian limit, the Galilean boosts were completely decoupled, but just drop them. In this case, something similar happens, but that would more generators. So if I construct a connection for the Poincaré symmetry like before, and I take the limit in the gauge fields, I will find a gauge connection taking values on this Fracton symmetry. From here, I removed the generators that decouple just to save some space, because this K and J and GA, if I add them, then through the analysis, I will obtain terms in the action that are totally decoupled from the Fracton gauge field, so I don't care about those. And if I can construct the curvature associated with this connection, then I find here exactly this F that I was showing you before that helps to find the Fracton electrodynamic actions from something relativistic. I can solve this as I showed before. Now something a bit more general. I obtained the symmetric tensor in the expression of the connection associated to the dipole. And I would like to interpret AAB as the Fracton gauge field, the symmetric Fracton gauge field that I showed you at the beginning. I also need to impose this gauge fixing that comes, it's inspired from this toy model that I showed you. And there is a compatible gauge fixing for row upper index, and that allows me to derive the fractal transformations from the gauge transformations of the original system. And now, if I start with a connection in 5 dimensions for the Poincare symmetry, I use this invariant tensor for the Lorentz group in 5 dimensions, Lorentz algebra in 5 dimensions, and construct this action. I can use the rescaling that puts together the Carolian idea, pseudo-Carolian, let's say, because it's on space plus Aristotelian on the gauge fields. So this is the dual rescaling for the gauge fields that comes from this rescaling of the generators. And I obtain an action that now lives in 5 dimensions. So the last step in this construction is to remove it by means of Kaluza-Klein reduction. So how much time do I have left? Okay. So yeah, so the last thing, okay. So I just want to briefly review the idea of the Kaluza-Klein reduction. So if one starts with 5D general relativity, for example, and one would like to compactify this 5th dimension, so one first would impose the condition that all the fields are periodic in the 5th dimension. Then one can expand on Fourier modes. But then if the compactification radius is really small, all these fields that appear in this expansion are massive, and the mass is proportional to the inverse of the compactification radius. So if the mass is too big, I can decouple these fields from the massless ones, and I can truncate these expansions at n equals 0, which means at the end that the gauge fields are completely independent of the z direction. So if one does that and one uses the standard answers for the metric in 5D in terms of a 4-dimensional metric, a vector and a scalar field, one can reduce 5-dimensional general relativity to a 4-dimensional action that contains the Einstein-Hilbert term, a dilatonic field, and a Maxwell action. So now I would like to do something like that in the case of the 5D theory that I showed you before. So if I start with this theory and I play the same trick, where in this case, well, I could remove the scalar field that I showed before. In this case, the field equations don't allow you to remove the scalar field, but in our case, it is possible. So then, if one follows the same idea of defining the Kaluza-Klein reduction, fixing the gauge in the way I showed you, and implementing the rescalings of the relativistic gauge fields, then one finds this expression for the action, where the first term gives a gravitational action that goes like the Riemann tensor squared, and the second term is exactly this Fracton electrodynamics theory with the term that goes with the Riemann tensor that I showed you at the beginning, but now constructed like from this high dimension. So this is like the result that we're now trying to understand, and at some point to publish. So the conclusions, we have considered the problem of defining Fracton gauge fields on pure geometry, which has a lot of problems. New action was found, which involves the Riemann tensor, but also imposes a constraint on the geometry for it to be a gauge invariant. We showed that the Fracton or dipole algebra can be obtained from the Poincare symmetry using a suitable nonlinear construction. And by gauging this symmetry, it's possible to construct a 5-dimensional action that yields Fracton electrodynamics after using a Kaluza-Klein reduction. And some future directions would be to maybe study different types of fractons by studying the representations of the Poincare group in 5D, or to consider different, maybe interesting backgrounds for this action, like, for example, a black hole metric, because the Schwarzschild metric satisfies this constraint, for example. So I could try to think if it's possible to understand or make sense of fractons on a black hole or something like that. So yeah, that's all.
Questions?
Can I ask a very simple question?
Yeah.
Why did you
Well, the name, but I think it comes from this restricted mobility. Yes. So
in a fractional part of the space, they can
Yeah.
move only
in these lattice models, they are constrained to move on a plane, for example. Of yeah. So
Fractional part.
It's not just an
These are highly unusual.
There's nothing to do with fractal.
No, that's nothing to do with. No. That's why no, it is a computer. It's more like yeah, it should be a fractional in the sense of
fractional mobility somehow.
fractional mobility.
Yeah.
So there's some ability, even your ability one day.
Yeah, exactly.
That's just nice.
Yeah, no. It's not. That's why they look
Mhm.
like a little bit like a model with dislocation. It's like a dislocation and only in one direction. Like some crystal dislocation that have some preference in one direction.
But it could also happen with this was the latest case, but it's not.
Yeah, exactly. Yeah, so these are highly constrained. Yeah, the point is maybe if I can emphasize the point, so that they are highly constrained because there are two Gauss laws basically. Right? There is the Gauss law of the charge, and on the top of that is highly constrained at the gauge theory. That the Gauss law for the dipole. Then you, as in terms of gauge theory, that they are
Yes.
so constrained that they cannot move the excitation. There are too many constraints. That's the problem.
But it's also do that like.
Yeah, no, exactly. That's why exactly. So there is some.
Well, it's not, I suppose, one dipole, you know, it's considered a dipole.
Yeah. No, at the microscopic level, there are no gauge field. That's why we started from lattice model. There are some lattice dipole, and they they can move on with it. But you can imagine to have also quadrupole conservation, octopole conservation. So it can be arbitrary. That's why one end up with the higher rank tensor. The simplest fractals, but in principle.
Yeah, but can go to like
Your example field that you looked for was one where the dipoles
Yes.
move arbitrarily in any direction.
yeah, but you could also start constraining those.
They didn't really pick out a direction.
That's true.
Mhm.
Yeah, but they didn't pick up. They didn't pick out things like that.
They picked out a space like hypersonics.
Yeah,
There was-
exactly.
They weren't really.
So you break lines through this.
Yeah,
No, there was no
That's
Lorentz. I'm just wondering in your lattice models, is there really a motivation for that?
In the lattice model.
For such a field theory, for like field theory where
Well, this theory is not really related to this Fracton lattice model,
These
but
are- okay, those ones not to be precise exactly. The effective field theory of this lattice model we presented are even easier. They are described by some scalar field, like the Ising model. Okay, the Ising model, the effective field theory is the field port.
yes,
In this case, it looks like a scalar theory with higher derivative. So you end up with some higher derivative of field theory for scalars,
okay.
or in this case, a gauge field. You also have some higher derivative. The crucial point that you end up with some higher derivative gauge theories, and they break Lorentz in all these situations.
But the parameters are such that you can get them to be to have low energy excitations relative to the lattice spacing.
Yeah. So in the lattice, you keep.
You need to motivate a continuum limit. You
No,
need to be
right,
able to get.
that's right.
Exactly. But all this stuff, so Cyber has done a lot on this precise derivation of the field theory from the lattice from the scalars. So it is really working.
But also one thing here, I didn't consider matter fields here because one could try to couple, for example, a scalar field. There is an action it's also involves more derivatives, and this scalar field action can be coupled to these gauge fields by means of generalized minimal coupling.
Yes, so you can have a scalar with this.
So this will be just the theory for the gauge fields, like mediating interaction between the Fracton matter fields. That would be,
I think
and then one could try to relate to the lattice, right?
Yeah, exactly. But one of the open questions is how to do fermions. So how to define the fermions covered to this kind of field. Nobody so far has done this. I mean, it's very complicated to think how fermions, even though relativistic fermions, can be fit in this context. So most of the things are done on the scalars, gauge theories, but everything was on it.
But you just even without stepping out of this, what are the excitations? What are the propagating degrees of freedom looking in this case? If I did a low momentum expansion, what do the waves look like?
Yeah, that's a hard question. I mean, the propagator for this field theories, they are not they don't look really physical. I mean, the theory is not Gaussian for the scalar field, for example.
It's not Gaussian, but I can do a small fluctuation analysis along. I just expand it out, and you've got the quadratic order in your AIJ. I get some sort of.
But I haven't looked at that detail, but I think
massless modes.
I think you cannot define really a pole in propagator, right?
Wait, so all these what you presented are all gapless,
They're gapless.
massless.
They are gapless. Okay.
Gapless, yes.
Yeah, whereas in the lattice they are gap models.
Yeah, because these other models are gap. So there are gapped fractons and gapless fractons. There are there.
Well, maybe this one in some background could be also gap because of this. Because of this, yeah.
In flat space.
Yeah, in flat space.
Yeah, eventually, people will use a mass.
They are gapless,
Yeah, they're gapless fractons.
but they don't move.
Well, that's why, because there is ultra locality, CO light goes to so localizing their mass. But again, they can move in couples.
Oh, there is a question here. I see someone.
Oh yeah, that's Venus. Yeah, sorry.
If I may, yeah, no, I'm enjoying the conversation. This may be a stupid question, but with these fractons coupling to gravity, could they have any implications for the inflationary period? Could they be driving inflation?
Oh, I have no idea. Wow. Well, some people are trying to relate fractons to gravity itself, right?
But you have to break Lorentz. So if I can say, so if you want inflation with this, you have to break Lorentz symmetry.
Yeah, since it involves a symmetric tensor of rank 2, so the action sometimes can be related to like Fields-Pauli.
Exactly. No, indeed, some fractal looks like linearized gravity. There are some, they are very similar. They are not equivalent. There is a sort of, they are relative.
Yeah, but this is a nice question, but I don't know. Yeah.
Thank you.
People have said also anomaly flow for this fractal. So there is going on also anomaly. I mean,
yes.
Bulk edge corresponds what we do around. I mean, the community also in IMPs are quite active.
And anomalies without Fermi.
Yeah, exactly. Like, The problem is that some people propose a supersymmetric verse, only with supersymmetry actually can fermionic degree, no? Then you have to break Lorentz, and then you have to go physically to this Cabrolian limit. So you have to
limit of your super.
So exactly, you take soda, you try to pin that and see go to the other. And this is something you can play it. It's to avoid it.
Yes. Well, they
So
appear.
you mind repeating the question?
Yes.
Yeah, I can't hear the question. If you could repeat it, please.
Or you can repeat
I just want to know what is
the motivation for considering fractals. Well, they appear in these theoretical lattice models. So people started wondering how this could be. I mean, if there is some field theory that captures these properties. I think they can define like new phases of matter, right?
Yes, it's sort of theoretical.
Yeah.
But there are also some connection with elasticity. So people that mark as a fractal.
Oh, yeah, that's right.
Elasticity theory.
Yeah, there is some sort of dictionary between elasticity theory and this fractal electrodynamics, where the charges are associated to these locations.
Yeah, that's why I mentioned it.
And and the dipoles are disclinations.
Yeah,
in
exactly.
this sense.
So you can associate,
maybe in this sense, yeah.
And even classical material, this kind of excitation.
Yeah.
I mean, look, in principle, there are many applications. People, as I said, they try to apply also to see some topological. They build some Simons like here that you like.
Also, yeah.
So
and holography and things like that too, right?
So experimentally, there are no symmetrics much.
Yeah.
So for real experiment, right? Right.
doing some theory or related some actual credits matter of the common number.
Good. No, that's why it's more about for condensed matter application. It's more about defect. Understand, new phase theory for defect, say, or also phase transition eventually. Maybe there are some because some of these are gapless. So maybe one of these, for instance, is a critical theory that breaks Lorentz, but could be a phase transition in some many body systems.
And there's also a motivation that you mentioned, like when people study the Fracton quantum Hall effect, there are some. Sometimes one cannot recover this Fractonic continuity equation, for example. So maybe some of these modes are Fractonic. That's what I don't know how far people are pushing this.
Again, there are some. It's just because you are using this higher rank symmetric times, right?
Yes.
So this is something that people can do. Even in soft matter, there are some kind of.
So maybe that could be a nice motivation. So there are some collective excitations in the fractional quantum Hall effect that have spin 2. They are massive.
Right,
but
I think there are already a couple of years about Fractons. So it's about talking to people. In a sense, it is something that is shared. Sort of topic for both condensed matter and people talk about holographic eventually build an holographic quality without Lorentz symmetry and application of this Caroline gravity. But, also your community is doing a lot about more relativistic gravity.
That relate this immobility coming from the ultra relativistic limit and the mobility. I think it's different, but
right. It's moment.
Questions? Let's thank.
Thank you. Thanks a lot.
Okay. Then I will stop the recording. Okay, thanks.